Welcome all. Today we will look into the Coriolis component of acceleration. Here, when a point on one link is sliding along another rotating link, when a point on this particular link OA, that link is rotating. That link is a rotating link. When a point on one link is sliding along another rotating link, here the rotating link is OA and another point or one slider is sliding over that rotating link, such as in quick return mechanism or a quick return motion mechanism. Then the Coriolis component of acceleration must be calculated. Here this omega is equal to angular velocity of the link OA. Angular velocity of the link OA is equal to omega. V is equal to velocity of the slider B. Here B is the slider, and C, this C is the coincident point on the link OA. Here this point C is the coincident point of this particular slider on link OA. But B is the slider and C is the coincident point on the link OA. Here omega is equal to angular velocity of the link OA. V is the velocity of the slider B at time t seconds. Here again at time t seconds. Then omega r is the velocity of the slider B with respect to O. Velocity of the slider B with respect to O. That relative velocity is omega r, and that must be perpendicular to link OA. That is also at time t seconds. And the corresponding values at time t plus delta t seconds. After a short interval of time delta t, these values omega v will become v plus delta v, and omega r will become omega plus delta omega into r plus delta r. Corresponding values at time t plus delta t seconds. Okay, next, let us now find out the acceleration of the slider B with respect to O. Acceleration of the slider with respect to O and with respect to its coincident point C. We can calculate velocity of slider B with respect to this coincident point C and the acceleration of the slider B with respect to the coincident point C and the acceleration of the slider B with respect to O. We can calculate that two accelerations separately. Here figure B shows, this particular figure B shows the velocity diagram when their velocities v and v plus delta v are considered. Here in this diagram we can see that the velocity v is along OA. Then we can represent that velocity here. That must be parallel to link OA. Then after a time interval of delta t, we can see that v plus delta v is along OA1, along OA1, that we can represent that v plus delta v is like this: OB1, O small letter b1. Here v is represented by OB. Then we can find out that delta v here, vector delta v is like this dotted line is represented by this dotted line. Then we can find out the component of change of velocity bb1, the components of change of velocity bb1 along OA and perpendicular to OA. Here this is the change of velocity delta V. Then that change of velocity have two components, one along OA and another one perpendicular to OA. Then we can draw a horizontal line like this and vertical line like this. Then we can find out that a vertical component or the component along OA is BX, and component which is perpendicular to link OA is B1X. Then Bx is equal to, from this triangle we can say that Bx is equal to, here Bx is equal to Ox minus OB. That's equal to, here Ox is equal to, this is V plus delta V. This part is V plus delta V and this is equal to delta theta. Then Ox is equal to V plus delta V cos delta theta. Then that minus V, that minus OB is equal to V. Then since delta theta is very small, we can therefore substituting cos delta theta as 1. Then Bx is equal to V plus delta V into 1 minus V. That's equal to V plus delta V minus V. That's equal to delta V. That is equal to delta V. Then we can represent that Bx as delta V. When this delta theta is very small, we can say that vertical component Bx is equal to that component which is along OA is equal to delta V. Then xb1 is equal to V plus delta V sine delta theta. V plus delta V, this part is hypotenuse. Then that b1x is equal to V plus delta V sine delta theta. Then since delta theta is very small, we can substitute sine delta theta as delta theta. Then this equation will become, V plus delta V into delta theta. That's equal to V delta theta plus delta V delta theta. Since delta V is very small, then delta theta also very small. We can ignore this particular value. Then we can say that xb1 is equal to V delta theta. Then we can say that a component of change of velocity perpendicular to OA is equal to V delta theta. That must be perpendicular to OA. Here, then we have already discussed this figure B. Then coming into the figure C, the velocity, this is the velocity diagram when the velocities omega r and omega plus delta omega into r plus delta r are considered. Here we considering the velocities of B with respect to O and velocity of that same slider after a time delta t, or after an angular displacement of delta theta, that point will become B1. Then that velocity of B1 with respect to O is equal to omega plus delta omega into r plus delta r, and that must be perpendicular to link OA1. Then we can represent that that velocity here, that is perpendicular to this position, and this velocity of slider B with respect to O at the initial position, that must be perpendicular to OA. Then we can represent that velocity here. This point O is at a rest. We can represent omega r along this direction, and omega plus delta omega into r plus delta r in this particular direction. This direction must be perpendicular to this link, and this direction must be perpendicular to this link. Then we can say that the change in velocity is this one, bb1. That change in velocity have two components, one along the link OA, another one perpendicular to link OA. Then we can say that the yb1 is equal to omega plus delta omega into r plus delta r. That means the hypotenuse of this particular triangle OYB1. That hypotenuse is equal to omega plus delta omega into r plus delta r. Then the sine component of that hypotenuse will become yb1. yb1 is equal to omega plus delta omega into r plus delta r sine delta theta. Then that's equal to omega into r plus omega into delta r plus delta omega into r plus delta omega into delta r, that all into sine delta theta. Since delta theta is very small, we can treat sine delta theta as delta theta. Then we can represent the yb1 as omega r delta theta plus omega delta r delta theta plus omega delta omega r delta theta plus delta omega delta r delta theta. Then we can neglect this term, again this term and this term, because delta theta already has small value, and that multiplied by another small value delta r will become very small. Then we can ignore these three values. Then yb1 is equal to omega r delta theta. yb1 is equal to omega r delta theta. Similarly, by is equal to by, that component which is perpendicular to link OA, that's equal to oy minus ob, that's equal to this one, that cos theta component minus omega r, cos theta component of cos delta theta component of this particular hypotenuse minus omega r. Then we can again, since the delta theta is very small, we can substitute cos delta theta as 1. Then by is equal to omega delta r plus r delta omega delta r plus r delta omega. Therefore, total component of change of velocity along radial direction is equal to bx, this component bx and this component yb1. Here bx is outward direction, and yb1 is in the inward direction. That means that total component of change of velocity along radial direction is equal to bx minus yb1. Bx is in the opposite direction of yb1. That's equal to bx minus yb1. That's equal to delta v minus omega r delta theta. That must be in the outward direction. Then radial component of the acceleration, that radial component is equal to limit rate of change of limit delta t tends to 0, then delta v minus omega r delta theta divided by delta t. That's equal to first term, limit delta t tends to 0, delta v by delta t is equal to dv by dt minus omega r into delta theta by delta t, limit delta t tends to 0 will become d theta by dt. That's equal to dv by dt minus omega r into d theta by dt. Here d theta by dt again, that's equal to omega. Then so that radial component of acceleration of b with respect to O, total radial component of acceleration of b with respect to O is equal to dv by dt minus omega square r, that will become in the outward direction. Then the total component of change of velocity along the tangential direction, that's equal to xb1, sum of this xb1 is in the negative x direction. Similarly, yb also in the negative x direction, so that the total change in velocity which is perpendicular to OA is equal to sum of this b1x and yb. That's equal to v delta theta plus omega delta r plus r delta omega, sum of these two values. Then the radial component, tangential component of acceleration of b with respect to O is equal to limit delta t tends to 0, this value v plus delta theta plus omega delta r plus r delta omega. That's equal to v into d theta by dt plus omega into dr by dt plus r into d omega by dt. That's equal to v omega plus omega v plus this one will become r alpha. That's equal to sum of these two values is equal to 2 omega v plus r alpha. Now radial component of acceleration of the coincident point C with respect to O acting in the direction of C to O is equal to radial component omega square r upward direction. Radial component of acceleration of coincident point C with respect to O. Coincident point C with respect to O is equal to omega square r. Then tangential component will become alpha into r, that the radial component of acceleration of coincident point, because that coincident point is on the link OA. Then radial component of acceleration of coincident point C with respect to O is equal to omega square r. We have already discussed that one. Then tangential component is equal to alpha into r. Then the radial component of the slider B with respect to the coincident point is equal to radial component of acceleration of B with respect to O minus radial component of acceleration of C with respect to O. Radial component of slider B with respect to coincident point. Because the radial we have already find out the radial component of acceleration of B with respect to O. Then we have discussed the radial component of acceleration of C with respect to O. Then the relative acceleration, radial component of acceleration of B with respect to coincident point C, that's equal to this radial component minus this radial component, or that relative value. Here that minus sign indicates that that radial component is in the opposite direction of this radial component. Okay, then dv by dt minus omega square r, we have already derived this equation, minus omega square r. Minus omega square r is the radial component of acceleration of C with respect to O. That's equal to dv by dt. Then tangential component, again same value, same equation. That's equal to 2 omega v plus alpha r, the tangential component of B with respect to O, minus tangential component of C with respect to O is equal to alpha r. Then we can say that that value is equal to 2 omega v. This tangential component of acceleration of B with respect to the coincident point C is known as Coriolis component of acceleration. That value is equal to 2 omega v. Coriolis component of acceleration of B with respect to C is equal to the tangential component of acceleration of slider B with respect to C, that is equal to 2 omega v, where omega is the angular velocity of the link OA and v is the velocity of the slider B with respect to coincident point C. Okay, then finally the direction of Coriolis component of acceleration. When this particular link rotating in the anti-clockwise direction and this slider moves in the outward direction, then that 2 omega v will become in this particular direction. That means negative x direction if OA is in the y direction. Then if that omega is in the clockwise direction and v is in the outward direction, then that 2 omega v will become like this. Similarly, when omega is in the anti-clockwise direction and v is in the inward or towards O, v is towards O, then the direction of 2 omega v, that Coriolis component will become like this. Then finally, this value is omega is in the clockwise direction and v is in the radially inward direction or towards O, then that Coriolis component will become in this particular direction. These are the direction of Coriolis component of acceleration. And the direction of Coriolis component of acceleration 2 omega v for all 4 possible cases is shown in this particular figure. Okay, that's all about Coriolis component of acceleration. Thank you. Thank you all.